Okay, this is our lecture for Chapter 3. We've already actually begun Chapter 3. We've done part of this, so I'm going to go quickly through the first part. Chapter 3 is about statistics. This time we're talking about numerical statistics, although we will talk about one more type of plot. Statistics for describing, exploring, and comparing data. And what we're going to look at now is we're going to learn how to summarize or describe the important characteristics of a set of known data. And in inferential statistics, we're going to learn how to use sample data to make inferences or generalizations about a population. We've already talked about measures of center, which is the measure at the value or center or the value at the center or the middle of a set of data. We talked about using words like average. A measure of center is a measure of average or typical or expected value. All of the following measures we discussed were measures of center. There's the mean, the median, the mode, and the mid-range. The arithmetic mean, which we just call the mean, is the measure of center that we obtain by adding all the values and dividing by the total number of values. It's what most people call an average. It's what you think of when you think of averaging your grades. Notation used here is, we refer to the data as X. X is the variable that we use to represent the individual data values. N represents the number of data values in a sample of data, or capital N if it's a population of data for some reason. It also is what is commonly referred to as the sample size, which of course is the number of data values. Capital N, as I said, represents the number of data values in a population. In notation, X bar is used to represent the mean of a set of sample data values, and it's pronounced X bar. It's an X with a line over it. The way we calculate X bar is we add up the data values. This symbol here simply is saying add up all the data, and then you're going to divide by the number of data values, which is lowercase n. The mean of a population is actually calculated exactly the same way. The only difference is that the mean of a population is given the symbol mu, which is a Greek lowercase m. And it's pronounced mu, mu. And it denotes the mean of all the values in a population. And again, all mu actually is the sum of all of the data values, which are the sum of the x's, divided by the size of the population, which is n. There are some advantages to the mean. The mean is relatively reliable. The means of samples drawn from the same population don't tend to vary as much as other measures of center. It does take every data value into account. However, because of that, that is one of the sources of its disadvantage, because it is sensitive to every data value. One extreme data value can affect it dramatically. So we say that it is not a resistant measure of center. The median is a more resistant measure of center because it's not affected by an extreme value. The median is the middle value when all of the original data values are arranged in order of increasing or decreasing magnitude. The mode, as we discussed, was the value that occurs with the greatest frequencies. Data values can have, or data sets can have more than one, or no mode at all. A bimodal data set will have two data values that occur with the exact same greatest frequency. Multimodal means that two data values occur, or more than two data values occur with the same greatest frequency. For example, you might have 3 modes or 4 modes or more. No mode means that there is no repeated data values. The mode is the only measure of center that can be used with categorical data. So here's some examples of the mode. In example 1, we have 5.40, 1.10, 0.42, 0.73, 0.48, and 1.10. And we see here that the data value 1.10 shows up twice in that list. Therefore, the mode for example 1 is 1.10. In example 2, we see that we have 3 27s and 3 55s, 2 88s, and 1 89. It isn't the fact that any values are just repeated. 88 is not a mode because it's repeated. It's only repeated. It's there 2 times. 55, on the other hand, is repeated 3 times, as is 27. So example 2 is an example of what we would call bimodal data. There are 2 modes, 55 and 27. Example 3 has no mode because the numbers 1, 2, 3, 6, 7, 8, 9, 10 each only show up 1 time. So therefore there is no mode. The mid-range, as we learned last class, is the value that's midway between the maximum and the minimum data values in the original data set. You add the maximum to the minimum and divide by 2, similar to the way that we find the midpoint of a frequency distribution for each one of the classes. You add the largest to the smallest and divide by 2. The disadvantage to the mid-range is that it does only look at those 2 data values. It doesn't look at all of them. It only looks at the extremes. And therefore, the extremes cause it to be very sensitive, and for that reason, it's rarely used. The example that we looked at last time was the price in dollars for a sample of room air conditioners, which were 10,000 BTU air conditioners. And the prices we found for the sample of 7 air conditioners were $500, $840, $470, $480, $420, $440, and another one for $440. And we found the mean, median, mode, and mid-range. Then we removed the outlier because $840 was a lot higher than any of the other data values. It was $340 higher than the next largest data value, which was $500. So we removed it and recalculated the mean, the median, the mode, and the mid-range. And this is what we saw. With the outlier, the mean was $512.86. Notice that in that case, the mean was higher than all but one of the data values. The median was $470, which was somewhat more in line with the values of the other air conditioners. And the mode was $440 because there were 2 air conditioners that cost $440. However, when we removed the $840 air conditioner, the mean dropped down to $458.33, which was a lot more reasonable value. The median did change because we went from having 7 to having only 6 data values. So the median turned out to be between the 440 and the 470 air conditioner, and that turned out to be 455. And the mode was unaffected because it still only showed up twice. It was the $440 air conditioner. So notice that the mean changed by $54.53, whereas the median only changed by $15. The outlier affected the mean more than any other measure of center, except for the mid-range. So one thing to keep in mind is that this time our outlier was an extreme on the upper end. It is also entirely possible to have an outlier that is extreme on the lower end, and that would have caused the mean to have been too low rather than too high. So we're going to do the calculator worksheet. We're going to actually work through the first problem. We're going to begin actually finding the measures of central tendencies and the measures of variation. So I'm going to pull up that calculator worksheet by going into Ch3, and your calculator practice is here. And what we're going to find, first of all, is the mean, the median, and the mode for the ages and months of a sample of dogs that visited the local dog park last month. So we're going to begin by getting the calculator, turning the calculator on, going to the Stat menu, delete out the data that I already have in List 1, and typing in the ages of the dogs. And of course, as we've mentioned before, you always want to be very careful that you go through the data and make sure that you typed it in correctly. So edit your data. And it seems that all of my data is correct. So now we're going to calculate the mean, the median, and the mode. The first thing we're going to do to actually be able to calculate the mean is we're going to press the Stat button again. We're going to go over to Calculate, and we're going to choose one variable, statistics. And even though if I didn't put in a list, since I have several lists there, I want to be sure that the calculator is using list 1. So I press the second and the number 1 button to specify that I want the one variable statistics for list 1. And then I press enter. The number at the very top of the screen, and notice this is a sample of dogs. The number at the very top of the screen says X bar, and that is the correct symbol because we have a sample of dogs. However, if this had been a population, you would be expected to know that the mean was actually the symbol mu, even though it would have the same value, 53.275. And you do not round the mean off unless you are specifically instructed to do so. So our mean is 53.275. And I was going to try to write it on there, but since I'm not using an iPad, that's going to be rather difficult. Be sure, though, that you do write in there that the mean, X bar, is equal to 53.275. The reason that's the mean is because the calculator added up all of the dogs' ages, and that's where it came out with 2,131, because that's the total of all the ages of the dogs in months, and it divided by the fact that we had 40 dogs. So if you were to take 2131 and divide it by 40, you would see that that is in fact the correct mean. The calculator actually also calculates the median, but it isn't on this screen. The arrow next to the number N indicates that there's more information below that value. So if you scroll down, you see some other information about these dogs. Some of the various information here is that the youngest dog was 8 months old, the oldest dog was 164 months old, and the median age of the dogs at the park was 47 months old. So the median, which has no symbol, the median age of the dogs was 47 months. We can't find the mode from one variable statistics. In order to find the mode, we have to go back to the stat button, and we will have to sort by choosing option 2 the values in list 1 into ascending order. And then when we go back and press the stat button and press the enter button to edit, we notice that the dog's ages are now sorted from the 8-month-old dog in ascending order to the oldest dog, which was 164 months. In order to find the modal dog's age, or the mode, what we'll have to do is we'll have to go back through the list and we'll have to count any dogs that showed up of the same age more than once. So we scroll carefully through the list, and so far I see 2 25-month-old dogs, and I see 2 26-month-old dogs. But I see 3 38-month-old dogs. So right now, 3 is the candidate for the mode, unless I see something that shows up more often than 3 times. So now I know, having scrolled through all the data and looked at the counts, that the mode for the dog's ages is 38 months, because 3 of the dogs were 38 months old. So the mean we determined what the mean was, the median, and the mode was 38. We can also, while we're here, as a way of introduction so that you know what's coming up, we can go ahead and also know what the range of the dog's ages was. That's actually quite easy to find, because when we look at the dog's ages, we see that the minimum age of the dog was 8 months old, and the maximum was 164. So the range of the dog's ages is 164 minus 8. And 164 minus 8 is 156. So the range of the dog's ages was 156 months. The other thing that we're about to calculate, and I will go ahead and recalculate the descriptive statistics so that you know that the formula is not the way we're going to go. The standard deviation of the dog's ages, which is this value here, is 34.69204261. I'll show you the formula for calculating that, but you will never have to actually calculate that by hand. The calculator will calculate that for you. And in this case, it's okay to round off your standard deviation. If you are not told otherwise, you want to round your standard deviation off to 2 decimal places more than your raw data. And since my raw data here is actually in whole months, then I would say that the standard deviation of the dog's ages, which is S, the calculator uses the X, but the symbol for standard deviation is S. The standard deviation S is 34.69, or in some cases it would be okay to round it off to 1 decimal place and say that it's 34.7. You would never round it off to a whole number. You would never say the standard deviation is 35. I'll return after we've discussed standard deviation and explain how to find the variance from what we have here. So let's go back to the PowerPoint. And let's talk about weighted means. When data values are assigned different weights, we can compute what's called a weighted mean. The way that we do this is with this really odd-looking formula, and basically what this formula tells us to do is to multiply each weight by the corresponding value of X, and then add all those products together, and then divide that result by the sum of the weights. It's really much less complicated than it sounds like it is. So, for example, one of the weighted means you're probably going to be the most familiar with is called the weighted mean of your grades. You know that your grades in this course don't all carry the same weight. So the way that we would actually calculate the weighted mean for some grades is, in this particular class, the test average, and this is not statistics, so don't take this as how you find your stats grade. The test average is 50% of your grade. Lab assignments are 10%, homework is 5%, the midterm exam is 15%, and the final exam is 20%. You want to find your final average. So you have your test average, which is 86, your homework grade is 100, your lab average is 98, the grade you made on your midterm is 96, and you made an 82 on the final exam. So this is how you would find your weighted average. The sum of the weights is going to be 100%, because 0.5 plus 0.10 plus 0.5 plus 0.15 plus 0.20 is actually 100%. So the way that we're going to actually calculate this weighted average is we're going to take 0.5 times your test average, which is 86, plus your homework grade is 100, but homework only counts 5%. So 0.05 times 100. Your lab average is 98, and it counts 10%, so 0.1 or 0.10 times 98. Plus your midterm was 96, and it counts 15%, so 0.15 times your midterm grade of 96, plus 20% of your grade is your final exam grade, and you can put that as 0.20 or 0.2, and you made an 82 on the final exam. So that's the sum of your weighted average And you would, I think I've typed something in wrong. Let's pause. I see what I did wrong. I see the error. I'm going to repeat the calculation and show you where I messed up. So that should have been 0.5 times 100 plus, not times, 0.1 times 98. And your weighted average is 88.6. Now there is an easier way to do this, and I'm going to show you the easier way to do this. You go back to your Stat button, and you go to your Edit button, and over in List 2, which I'm going to delete all the values out, I'm going to type in your grades. And I'm going to begin with your test average, which was 86. And then the lab assignments are 10%, so I'm going to enter in your 98 points for your lab average. Your homework average is 100, which is going to count 5%. And your midterm was a 96, and your final was an 82. Then, over in the next column, I'm going to type in the weights, and I'm going to type in those weights as decimals. So 50% is 0.5 or 0.50. Lab assignments are 0.10. And even though I type in 0.10, it changes it to 0.1. Homework is 0.05. Don't forget that 0 in front of that 5%, because 50% and 5% are not the same thing. And the midterm is 0.15. And the final exam is 20% or 0.20, which it truncates that to 0.2. And as long as I include both lists, my calculator will calculate the weighted average. I simply hit Stat, go over to Calculate. You still want one variable, statistics, because the variable is your grades. You hit Enter. We actually put your grades in List 2, but it's a weighted average, so we add a comma, and then we enter the column, which is List 3, where the grade weights are included. And we hit Enter. And notice here it still tells you, as it did before, that your weighted average is 88.6. Now we're going to talk about measures of variation. Measures of variation are measures called the range, the standard deviation, and the variance. So that you'll understand what these are and why do we need to consider both variation and center in a data set. Imagine you supervise 2 deli managers that sell bacon. Since you don't want any of the bacon to be wasted, because let's face it, it's a crime to waste bacon. Everything's better with bacon. It's important that these 2 managers hold a steady inventory. So in an effort to measure how well they manage that inventory, we're going to analyze the boxes of bacon that each manager ordered in the last 6 weeks. And then we're going to take the average of the last 6 weeks, and the average is going to show that each manager orders an average of around 32 boxes of bacon a week. On the surface, the averages alone make it look like they're performing equally. However, here's the actual data. And what you notice here is that manager A, we'll call him or her, is pretty consistent. Their orders don't vary much each week. They're mostly in the 30s, which leads to the average of about 32.3. Manager B, on the other hand, goes from 22 cases one week to 34 cases to 58 cases, and then 52 cases, which means the following weeks that he or she only orders 10 and 21. So there's a lot of variation in manager B and a lot less consistency in his ordering amounts. The standard deviation is a measure of that variability. So we're going to find the variation of both managers, and we're going to use the calculator. So we go back to the stat and go to edit, and in list 4 I'm going to enter manager A. And in list 5, I'm going to enter the orders for manager B. And now we'll calculate the one variable statistics for both managers. So here we see manager A's average is 32.3, rounded to the nearest tenth. But the standard deviation for manager A is 1.966, which we'll call 1.97. So that's a standard deviation of right at 2 boxes a week. And if you look, the variation in order from week 1 to week 2 was about 2 boxes. From week 2 to week 3 was only about 1. Then week 3 to week 4, it was about 4 boxes, then back down to 31 and 31 for the next 2 weeks. So that means that overall, the data varied by around 2. It's actually a measurement of how much each value varied from the average of 32.3. So you can see that 33 varied by less than a pound, 31 varied by about 1 1/3 pounds, 32 by only 3/10 of a pound, 36 varied by more like about 3.9 pounds, 31 was a variation of about 1.3 pounds, and 31 again was a variation of about 1.3 pounds. So the standard deviation you could think of as kind of like an average of the individual differences of every data value from the mean. Now let's look at manager B. And again, we're going to hit stat. We're going to go to calc, choose one of our stats, and manager B's data is in list 5. And we see that manager B's average, again, is 32.8, not much different from 32.3. But manager B's standard deviation is 18.87, or about 18.9 boxes a week. And you see that just from the first week to the average, there's about 9.2 boxes difference. And in the next week, there's a lot less. There's only about 1.2, but in the following week, 58 minus 32.8 is 16.8 boxes difference. And 52 minus 32.8 is 20.8 boxes difference. And then 10 compared to the 32.8 average is 22.8 boxes difference. And then 21 is actually 11.8 boxes difference. So notice there's a lot more variability in manager B's ordering methods. Now you might say, well, why does that matter? Well, if this manager is ordering pretty consistently the same amount of bacon, then his bacon is turning over regularly, and his bacon is pretty much fresh every week. This manager apparently ran short on bacon, so tried to compensate the next week, and apparently still ran a little short. So the next week he ordered more than 20 pounds or 20 boxes more bacon than before. and then another almost 20 boxes the following week. Well, these boxes didn't sell. So even though he orders 10 more and then 21 more, all of this bacon is probably sitting on his shelf, and probably by the time we're selling this bacon, some of this bacon is old, and customers don't want to buy old bacon, and eventually he's either going to have to mark that bacon down to sell it, or he's going to have to actually write it off and throw it away because it's going to go bad. So that's why consistency, which is a measure, it's measured by variation or standard deviation, that's a very important measure. Now there's another measure of variation, and that measure of variation is called the range. The range is the maximum minus the minimum. The problem is, like it is with the mid-range, it only takes into account the maximum and the minimum. It's very sensitive to extreme data values, and it's not very useful. If we move back to our managers buying bacon, we notice here that the range for manager B is 58 minus 10, which is 48 boxes, whereas the range for manager A is 36 minus 31, which is only 5 boxes. So again, much less variability, but again, we only look at the 58 and the 10 and the 36 and the 31. You really can't tell much about what else is going on if we only use the range. So we calculate the standard deviation. You see we've already calculated standard deviation. The way that it's actually calculated, if you have a sample, is you take the mean from each one of the data values, and then you square those differences. The reason that you have to square them is because if you didn't square them, what happens is that because it's a weighted average of the distances, then some of the distances are negative, some of the differences are positive, and they cancel each other out. So if you just add up the differences of each data value minus the mean, it actually always adds up to 0. So what we do is we square those in order to keep that from happening. And then because we square those, and also because it's a sample, we divide by n minus 1. But because we square those, we have to take a square root to remove the enormous amount of change that we introduce by making those numbers so large by squaring. The only difference in the standard deviation of a sample and the population is that the sample you're going to divide by 1 minus the sample size, whereas if you have the population, you're not going to subtract that 1. The standard deviation basically takes into account the spread of all the data around the mean. A small standard deviation indicates little variation, and a large standard deviation tells us the data values are more spread out. For example, a data set having a small standard deviation might be the amount of money that a student spends on average every day if they eat lunch every day at Subway. Because most students eat maybe not the same sandwich every day, but they eat approximately the same thing every day. If you get, a 6-cent sandwich every day, some days that sandwich is going to be $3, sometimes it's $4, sometimes it's $5, but it's not going to vary overall very much every day. A set of data that might have a very large standard deviation, on the other hand, might be the salaries of all the people that work for the company, like Eastman, because there you have people that have basically menial jobs, the people that are custodians, data entry clerks on the lower end of the scale. Then you have some mid-level people that make more moderate salaries, but then you also have some CEOs, some vice presidents, and some presidents of the company that make 6-figure and higher than just 6 figures. I mean, they make probably as much as close to $500,000 or $1 million a year compared to the people that are making $10,000 or $12,000 a year. So that set of data would have a very large standard deviation. A set of data having a standard deviation that would be 0 would be the amount of money that I spend on my way to school every day, stopping at Starbucks to pick up my coffee. Because I order the exact same cup of coffee every day, and it costs me the exact same thing every day. So my daily coffee bill for 5 days a week is going to be $2.18 a day for 5 days. And if I add up $2.18 every day and divide by 5, I'm going to get $2.18. And if I do the standard deviation for my 5 $2.18 cups of coffee, I'll leave it to you to check out the fact that the standard deviation, in fact, is 0, because I always spend the same thing on my coffee. Variance is not a very useful measure of variability because of the fact that it is actually the square of the sample standard deviation or the population standard deviation. If we return now to our example, our worksheet with the dogs, if you remember, here's the dog weights. And I still have the dog weights in my list, so I'm going to hit Stat and Calc, and they're still in List 1, so I'm going to recalculate the statistics for List 1. And I see that my standard deviation for my sample of dogs was 34.69204.261. That means then that the variance for my set of dog weights would have been 34.69204.261 squared. And I could actually sit here and type in 34.69204.261 and square it, and I will have the variance. What you do not want to do is you don't want to take the rounded off variance, or I'm sorry, the rounded off standard deviation and square that, because if you notice here, it introduces just a little bit of error. Now there is another way to calculate the variance. There is a menu. If you press your VARS button, and you go down to number 5, Statistics, there is a menu of all of your statistical formulas here. And if you would like to calculate the variance without having to type in all of those digits, you can simply select item number 3, which is the sample standard deviation, and you square that, and it gives you the correct answer. And this one is a totally not rounded value, so notice there's just the tiniest bit of difference between those. But that is how you calculate variance. You square the standard deviation. So at this point, we're going to move on, and I'll have to refresh my page because it's lost itself. And I apologize, my computer is very, very slow. And now we're also going to calculate mean, variance, and all of that from a frequency distribution. So we're going to pop back to the PowerPoint for just a moment. And we're going to find the measures of center and variation on the worksheet, and we're going to work from the calculator on the frequency distribution. So here's how we're going to have to do this problem. The issue here is that we do not have a single value for these 10 numbers. We've summarized our data. This is the ages in a particular Math 1530 section. And we had 10 students from 17 to 22. We had 6 from 23 to 28. We had 3 from 29 to 34. We had 4 from 35 to 40. And we had 2 between the ages of 40 and 46. And we need to calculate mean, standard deviation, and so forth, but we don't have the actual raw data. We can still calculate those values. This is how we do it. You go to the calculator and you go to your edit menu. And at this point, since I'm finished with the weighted grade data, and I'm finished with the dogs data, I'm going to actually clear those two out. And just for the sake of not having the extra column on that page, I'm going to clear out that one too. In list 1, the only way I can estimate the ages of those 10 people that were somewhere between 17 and 22 would be to estimate their ages as the midpoint of that class. And if you remember, the way you find the midpoint is that you add the two up the lower class limit to the upper class limit and divide the sum by 2. And you can actually do that right straight away on your calculator. So I'm going to add 17 plus 22, divide that by 2, and get the age of 19.5. Now I can continue doing that. You do need the parentheses. 23 plus 28 divided by 2, because you want to be sure it adds before you divide. And the same thing, I can do it again, 29 plus 34. But I would also point out to you that if you pay attention to your class width, 23 minus 17 was 6. 29 minus 23 was 6. 35 minus 29 was 6. 41 minus 35 was 6. My class width is 6. 19.5 plus 6 is 25.5. Plus 6 is 31.5. Plus 6 is 37.5. Plus 6 is 43.5. And I don't have to continue to do those. Now, you can do that either way that you want to. But the point is, you need the midpoint of all your age class limits. Then in list 2, just like we did with the weighted average for the grades, we're going to enter the frequencies. 10 in the first group, 6 in the second group, 3 in the third group, 4 in the fourth group, and 2 in the last group. And then we're going to go to the Stat button and over to calculate one variable statistics, again, because the only variable is the ages. Frequency is not a variable. And the variable for the ages is listed in list 1. But the frequencies that are tied to those ages in list 1 are in list 2. And we will calculate our statistics. And we see that the mean age for this class is 27.18. And we see that the mode cannot be found. Because since we don't know the actual ages, we don't know what the mode was. However, we can find what's called the modal class. The modal class is the one that has the highest frequency, or the most numbers of members in that class. And that would be the 17 to 22-year-old range. So the modal class, we would put down 17 to 22. We also can calculate the median. In fact, the calculator's already calculated it for us. But if you'll notice, the median in this case is 25.5. And the reason it's 25.5 is because the middle student is in this class. You have a total of 10 plus 6 is 16, 17, 18, 19, 23, 24, 25 students. So the middle student of 25 students is going to be the 13th student. Well, if there's 10 in this class and 6 in this one, the 13th student belongs in that class. And since we don't know exactly how old that student was, we have to assume that their approximate age was 25.5. Similarly, that's why that the minimum age is 19.5, because we don't know who the actual minimum, what the actual minimum age was, although we could probably presume it was 17. And the maximum, we can't presume it was 46 because it may have only been 45 or 44. So we're going to assume that it's the middle of the class. Remember, what these 5-number summaries for a frequency distribution of class midpoints is only going to be able to refer to the class midpoints. We can also calculate the standard deviation and the variance. The standard deviation, since this was a sample of students, is 8.219, which we would round to 8.22 and use the symbol S, unless we were to decide that this was for some reason not a sample. If we thought that that was the entire population or that section, which indeed it is, then we would say that the standard deviation for that whole class was 8.05. This is the population standard deviation, and it has the symbol sigma. And if that was the case, then we would say mu is equal to 27.18 for the mean, and sigma is equal to 8.05 for the standard deviation. And the variance, once again, would be whichever standard deviation squared. And since we're talking about all the students in that section, we're going to presume this is a population. So in order to find the variance, we take 8.05342163 and square that number and hit enter and get 64.8576. So the variance is 64.86. How many students were in the section? 25, because it summed up the frequencies and says there's 25 students in the section. How many of the students were 23 to 34? Well, 23-year-olds were in this group. 34-year-old students were in this group. So we have a total of 9 students from the ages of 23 to 34. What percentage were 23 to 34? Since we have a total of 9 students, 9 of those 25 students were 23 to 34, which is 0.08 or 8%. So the answer to your last question is 8% of the students were aged 23 to 34. So here we have another example. The flight durations and hours of a simple random sample of all the flights of NASA's shuttle. And we need to find the mean, standard deviation, and variance. So we'll go back to the data. And we're done with the frequency distribution, so I'll delete out that information. And there's frequencies. And since we don't have a frequency distribution, we have the actual data this time. We enter the data 73, 95, 235, 192, 165, 262, 191, 376, 259, 235, 381, 331, 221, 244, and 0. Don't leave out the 0. That is a data value. You cannot omit it. And then, since we're finding one variable statistics of the data that I've entered into list 1, the mean of the sample of 15 flight times, you notice here there's 15 flight times, was 217.3. It's not 217. It's X bar equals 217.3. The standard deviation is S is equal to 105.92. And the variance is 11,219.1. That's a rather large variance, but remember the variance is square of the standard deviation. So this is the duration in hours. That means the average flight time was 217.3 hours. The mean flight time was 217.3 hours, but that varied on average by about 105.92 hours. Now we have an interesting question here because we need to think about what values in that group might have been unusual, because remember we had a 0 in there. We have something called the range rule of thumb for finding unusual and usual values. It's based on the principle that for most data sets, the majority of the data in a set of data, the majority of the values will lie within 2 standard deviations of the mean. So the minimum usual value is the mean minus 2 times the standard deviation. And the maximum usual value is the mean plus 2 standard deviations. In the case of our flight times, we would take the mean of 217.3 minus 2 times 105.92 and find that the minimum usual time should have been 5.46 hours. And then repeating the same calculation, but adding 2 standard deviations, we would find that the maximum usual time is 429.14 hours. So if we went back to the data, we notice that none of the flight times is more than 429.14 hours. But there is a flight time that is less than 5.46 hours. And that means that that flight time is unusual because it would occur less than 5% of the time. Because 95% of the data values should have been between 5.46 and 429.14. So in answer to the question, if I can get it to sit still long enough, is the lowest duration time unusual? The answer is yes. Sometimes we need to compare two data sets. For example, in cost of living, one of the things that the cost of living index takes into account is things like the cost of a loaf of bread and the cost of an automobile. Well, it's hard to compare the the price of bread with the price of a car, largely because even though the standard deviation is very small, it appears, for the slice of bread, and a lot larger for the car, the thing is, the mean of the car was a lot larger than the mean for the price of the bread. So we would, in order to discuss which set has less variability, we have to be able to have a measure that would compare it appropriately because the means are not equal. So the way that we would do this is you only compare the standard deviations when the means are approximately the same. When we're comparing variation in samples with different means, it's better to use something called the coefficient of variation. And this is how we find the coefficient of variation. The coefficient of variation describes the standard deviation relative to the mean. So the coefficient of variation is calculated by taking the standard deviation and dividing it by the mean. And then in order to make it into a percentage, we're going to multiply it by 100. So the lower the coefficient of variation, the less variability there is in a data set. So for example, looking at the weights of the Atlanta Braves, let's try that one. We're going to enter some data. We're going to enter the weight and the heights of the Atlanta Braves. Their heights are 71, 75, 74, 72, 73, another 73, 76, and 72. Now their weights, on the other hand, are 220, 210, 220, 185, 175, 170, 210, and 175. What we would like to do is compare the two of them and see which is more variable, their heights or their weights. So looking at this sample of players, what we're going to do first is calculate the one variable statistics for their heights. So we see the average player is 73.25 inches tall, and that varies by 1.669 inches. So if I take 73.25 and I divide that by this, I'm sorry, I did that backwards. If I take the standard deviation of 1.669045921, and again, I'm emphasizing to you, you don't round anything off. You always keep all the digits until the final answer. And then we're going to divide that by the mean, which is 73.25. And then we multiply that times 100 to change it to a percent. And we see that the coefficient of variation for their heights is 2.2785, which we can round to about 2.3%. Now we're going to do the same thing for their weights. So we see the standard deviation of their weights is 21.45385413. divided by the mean of their weights, which is 195.625. And then we're going to multiply that times 100 to change it to a percentage. And we see that the variation in their weights is 10.96668. And that would round off to 11.0%. Be sure and round properly. But 11% is indeed a lot higher than 2.3%. So the coefficient for their height is 2.3%, but for their weight is 11.0%. Based on the sample data, there is less variation in the players' heights. So if we look at the same example here, we see with the price of the bread and the car, notice that the standard deviation for the bread's price was 0.30 divided by 2.19 times 100. And that's 13.7%, whereas for the car, the standard deviation was 2,000 divided by 17,900 times 100 to convert it to a percentage, and it was 11.2%. So actually, the car has less variability in its data than the price of the bread does. Percentiles are measures of location. There's 99 percentiles, P1, P2, P3, and so forth, all the way up to 99. If you had 100 people and you arrange those 100 people in order, the first person would be at percentile 1. The last one would be at percentile actually 100. The person behind them would be person at the 99th percentile. Percentiles divide a data set into 100 groups, and about 1% of the values are in each group. The main thing to understand about percentiles is how they're interpreted. If you're told that the weight of an infant child is in the 78th percentile, that doesn't mean that they weigh 78% of some ideal weight or anything like that. If a weight of the infant is in the 78th percentile, it means that that infant's weight is greater than 78% of all the infants that were in the same group. So there are 78 infants that weigh less than that child and 22 infants that weigh more than that child out of 100 infants. You could also say that the infant's weight is less than 22% of all the other infants. The most important percentiles we'll talk about are called quartiles. The measures of location are denoted as Q1 for the 25th percentile, Q2 for the median or the 50th percentile, and Q3 for the third quartile or the 75th percentile. Those three quartiles divide the data set into 4 groups. Think of quartile meaning the same thing as a quarter. A quarter's 25% of a dollar or 25 cents out of 100 cents. So the first quartile separates the bottom 25% of sorted values from the top 75%. The second quartile separates the bottom 50% from the top 50%. Q2 is, as I said, the same as the median. The third quartile separates the bottom 75% of the data from the top 25%. But again, remember that has to be rank ordered. Those are 3 very important members of what's called a 5-number summary. And we actually mentioned this before. We looked at a problem and calculated the 5-number summary. So we're going to do that again. But some definitions to go along with that. In addition to the 5-number summary, there is a measure of variability called the interquartile range. which is the third quartile value minus the first quartile value. The interquartile range, since the 25th percent mark is subtracted from the 75th percent mark, the meaning of the interquartile range is that 50% of your data values fall inside or between the first and the third quartile. Outlier data values lie very far away from the vast majority of the other data values. And basically, finding an outlier is going to mean we're going to look at that middle 50% and try to determine how far an extreme value is from that middle 50%, which is why we're going to be looking at the interquartile range. So here's a set of data that we've made a box plot from. In this data set, we don't know the actual values, but we know that the smallest one was 4.5. We know that 25% of the data was less than 35, and 75% of the data was more than 35. We know that half of the data was less than 68, because that's the median. So 50% was less than 68, and 50% is more than 68. We know that since the third quartile, or the 75th percentile, is 113, we know that 75% of the data values in this data set is less than 113. We know that 25% of the data values in this data set are more than 113, up to a maximum value of 225. We also know that 50% of the data values lie between 35 and 113. And looking at that, you can tell that 225 is pretty far from that middle 50%. So our question is this value 225 an outlier? In order to determine if that's an outlier, what we'll do is we will actually calculate the fences. And I'm going to go back one slide to show you how to calculate that. So Q1 minus 1.5 times the interquartile range. Okay, for the set of data we're looking at, the interquartile range is 113, which is the value of Q3, minus 35, which is the value of Q1. So the width of this box in the box and whisker plot is 78. So there are 78 potential values between 35 and 113. That is the interquartile range. When we multiply that times 1.5, we get 117. So if I add 113 and I go up another 117, that's going to put me roughly about here. In fact, 117 plus 113 is at 230. Okay? So 113 plus 1.5 interquartile ranges is 230. Is our maximum actually an outlier? And the answer is no, because it's lower than what we call the upper fence. And it's fairly obvious that 4.5 isn't an outlier because it's a lot closer to 35 than the 225 was to the 113. But if you wanted to prove it, then you would simply take 35 minus 117. And see that the lower fence is all the way down to negative 82. So we don't have any outliers in that box and whisker plot. This is a box and whisker plot of what would be an approximately bell-shaped distribution. Notice here that half your data is pretty much centrally located between the two endpoints of what are called the whiskers. And the whiskers are about the same length on either side as that middle 50% is. So the whiskers are about the same length as the width of the box. This data set is very, very skewed right because 75% of the data is less than 638.44, and yet we have a largest data value of 2,840. So if I calculated the upper fence for this set of data, I would take 638 and subtract the first quartile, which is 205, to get the width of the box, or the inner quartile range. I would multiply that times 1.5 because that's part of the formula. And then if I add 638.44, the third quartile, to the 650.16, I see that I only have, leaving out a zero makes a huge difference. I have 1288.6. Well, 1288.6 is a lot less than 2,840. So 2,840 in this case is an outlier. And we can tell that it's a skewed right distribution because the right whisker of your box plot is a lot longer than all the rest of the box plot combined. So what we've been talking about here is the outliers. This is a summary. Outliers are data values that lay very far away from the vast majority of the other values in the data set. To calculate the lower fence, it is Q1 minus 1.5 times the inner quartile range, and Q3 plus 1.5 times the inner quartile range. Outliers smaller than the lower fence or larger than the upper fence are found that way. Anything that's less than this or more than this is an outlier. And to give you an example, we're going to go back to a data set we explored before, back in section 2, when we looked at the female pulse rates. And those female pulse rates I'm going to put in my calculator. And I'm going to go ahead, and I'm actually going to clear these out all at once in the interest of time. So I'm going to enter these in. And again, I'm going to make sure that I enter them correctly. Okay, with some corrections now. I've got those entered correctly. And what I'm going to do is I'm going to have the calculator calculate the 5-number summary by doing one variable statistics. And I see the minimum value is 60, the first quartile is 68, the median is 74, the third quartile is 80, and the maximum is 124. And then you can also make this graph on your calculator. You first press your second button and then your Y equals button, and you choose plot 1. And on plot 1, you make sure it's turned on by clicking on the on. If it's sitting over here on off, then you want to move the cursor over here to on and click the enter key to turn it on. Move down, and the box plot that we want to make, we're actually going to make the first one because it's going to show us if there's any outliers. You can also make a second box plot that doesn't necessarily show you the outliers, but I want the one that shows us outliers if there are any. So we're going to choose the first one. Our data is actually in list 1. Oops. You have to click enter to actually select that box plot. Our data is in list 1. Frequencies you leave alone, that's just 1. And if there are any outliers, it's going to show us the outliers with a little box like that. And then the next thing that we're going to do, and I know we'll practice this. The next thing we're going to do is we're going to press the zoom key. And if you're making any kind of a statistics plot, when you press the zoom key, you go down to zoom number 9, which is zoom stat, and you press enter. And here we have the box plot for our data. And notice that we actually have 2 outliers. In fact, I'm going to show you the box plot on the screen. This box plot is the same box plot of those pulse rates. And I can trace on this one. If I press the trace button, I notice that it says the median of that data set is 74, which we already saw. If I move to the left, it says that the first quartile is 68, which we already saw. And that the minimum value is 60, which again we already saw. But if we move up here to the third quartile, it says the third quartile is 80. And it told us that the maximum was 124. Well, there's the 124 maximum. But the 104 and the 124 are both outliers. So the next lowest data value is the end of the whisker, which is a 96, which you see right here. Now, how do we know that those are outliers? Well, remember, the interquartile range is 80 minus 68. So that's 12. And if we multiply 12 by 1.5, we get 18. And that means that if we take 18 from the third quartile, and the third quartile was 68, then our lower whisker is 50, and our lowest value is 60, so it's well within the range. It's above the number 50. That's our lower limit for usual values here. However, if we take, I'm sorry, I chose the wrong, I'm sorry, yes, I did, that's the minimum. So that's our lower value. Our upper value of 80, if we add 18 to that, our upper fence is at 98. 104 and 124 are both larger than 98. Therefore, they are outliers. And then I'm going to leave to you to look at this example. Here you have the speed in miles per hour of the Cedar Point Amusement Park. It's known as the roller coaster capital of the world. And here's all the different roller coasters they have. And notice that the Wilderness Run speed is only 6 miles per hour. However, the speed of the Top Thrill Dragster is 120 miles per hour. So my question for you is, load that data into your calculator, create the 5-number summary, look at the box plot, and tell me, is either of those two, either the Wilderness Run or the Top Thrill Dragster, are those outliers? So that's for you to do, and you can ask me questions once you've got that done. Now, your assignment is to complete the Measures of Center worksheet in Ch3 and to complete the Manatee worksheet in Ch3. And we've pretty much completed the calculator practice worksheet, so if you haven't completed that, do that. But I will be grading the Manatee worksheet and the Measures of Center worksheet as part of your homework grade. I'm also going to go back and show you where there is another assignment you need to complete. And that's this one. This is for practice. It will be graded. This one, on the other hand, explains how to do that assignment. And it's actually very self-explanatory. I will try to go ahead and make a recording for you of this. But if not, just follow the directions. This is a lab on correlations. The first step that we're going to do is prepare the calculator. And actually, I'll just go ahead and go through this with you because it doesn't take long. So what we're going to do on the calculator is we're going to turn it on. And we're going to press the 2nd and the 0 button, which takes us to here. We're going to scroll down until we come to this option right here, Diagnostic On. And we're going to hit Enter. Then we're going to hit Enter again. You didn't see it do anything. You don't ever need to do that again. But in order for this to work for the rest of the semester, we do need to do that one thing. So be sure you complete those 3 steps. What we want to do to visualize correlation is we want to look and see if there's a correlation by looking at a graph called a scatter plot. We're going to create this scatter plot on the calculator. So I'm going to minimize that a little bit so we can see the calculator easily along with the handout. The data we're going to use is data about the number of times a cricket chirps per minute and the temperature outdoors in degrees Fahrenheit. So we're going to learn how to make a scatter plot of this data. A scatter plot is a way to compare a set of data that actually has 2 variables to see if there's a relationship between those 2 variables. So we're going to go to the Stat button and we're going to press Enter to edit. And I'm going to clear out all those pulse rates. And we're going to enter the number of cricket chirps in list 1. And then we're going to go over here to list 2, and we're going to enter the temperature outside where those crickets are chirping. So they chirped 1,043 times a minute when the temperature was 83 degrees. They chirped 960 times a minute when the temperature was 72 degrees. They chirped 1,200 times a minute when the temperature was 90 degrees. They chirped 1,188 times when the temperature was 94 degrees. They chirped 880 when the temperature was 70. They chirped 900 times when the temperature was 80. They chirped 860 times when the temperature was 76. And 1,100 times a minute when the temperature was 85. Now, looking at just the data, it's really hard to determine is there a relationship between how often they chirp and what the temperature is. So what we're going to do is we're going to create a scatter plot. And the way we're going to create the scatter plot is, again, we're going to press the second and the y equals button. This is where we made the box plot a few minutes ago. We're going to enter plot 1, make sure it's still turned on. Then we're going to go down arrow and we're going to change the plot from the box plot. We're going to change it to the first plot, which is called a scatter plot. Now you're going to press the zoom key, as is shown right here. We're going to press the zoom key and go down and select zoom 9. And we're going to press enter. And this is what we see. And does there seem to be a linear trend to this data? And what I'm asking is, do the points on the graph fall in a kind of an upward or downward trending pattern? And you see here that it does appear that the points are kind of traveling uphill. Now, they're not in a perfectly straight line. I'm not implying that they have to fall in a perfectly straight line. That isn't the case at all. But what we can infer by looking at that scatter plot is that there is a positive relationship, or there is a relationship. From this, we can infer there is a relationship between the number of times the cricket chirps and the temperature outside. And that relationship in a sentence is that, and remember, the temperature is the y-axis, the chirps is the x-axis. It does seem that the cricket chirps increases as the temperature increases. Now, the question of causality is not important here. Does the cricket chirping cause the temperature to go up? No. Is it possible, however, that the crickets chirp faster because the temperature went up? And yes, that is possible. But basically what we see is that as the temperature increases, the number of times the cricket chirps also increased. And that's really what I want you to understand at this point. Then the next thing I want you to do is go into My Math Lab and go to page 67 of your e-text. And I want you to begin reading section 2.4. These are some definitions that you're going to find in your book. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between the variables when there is a correlation. The plotted points of the paired data result in a graph that could be approximated by a straight line. This data could be approximated by a straight line. I'm not talking about connecting the dots, just that a line would fit kind of through the middle of those points. A scatter plot or a scatter diagram is the plot of those paired data. On page 74 of the e-text in My Math Lab, I want you to click on this icon, and I want you to work the 3 problems that are there, and then complete the following problem from page 75. So on the e-text, actually I need to go back one. The icon that I want you to click on is this one. Let's try that again. Oh, I clicked on the wrong one, sorry. I want you to click on this one for number 5. And I want you to view exercise 5 and take notes. If you need help, you've got your question help there. You need the data for the elections. You click on this button, and then you enter that into your calculator, and you determine which one of these is the appropriate scatter plot. Check your answer. Finish that problem. Repeat with exercise 6. And again, if you need help, you have question help. It'll help you solve it or it'll show you an example. And then the same with exercise 7. And the tech help will take you to using your graphing calculator to help you with this too. And the video that you would want would be this one. And it will walk you through exactly the same thing that I just did. So then the last thing I want you to do is I want you to, and I said complete the following problem and show your work. The problem I want you to complete is the problem that is at the top of page 75. I want you to complete problem number 8. So complete problem number 8 on page 75. So that wraps up our video. I will see you on Wednesday, and we will go over the practice test, and your exam over chapters 1 through 3 is on Wednesday. February 14th.